Here we're going to look at the differential equations that are material balances for containers. So let me pause and draw the system we're looking at. So we have a tank with some amount of material M. This M's total mass. And then we have a mass flow rate into the tank. And we have a mass flow rate out. And these in general are not the same, so that the mass in the tank can change with time. And our general mass balance accumulation is flow in plus generation minus flow out minus consumption. And what we're going to do is look at the system for some time delta t and say in that time there's a change in the total amount mass material delta M, and that's due to the fact that we have a flow rate in, so the amount flowing per time times delta T is the mass flowing in, and we have mass flowing out delta T. There's no generation and consumption. We're looking at overall mass balance, so this is overall. And we can divide by delta T. And what we do is then say if delta T is really small, this approximates a derivative, and that's equal to the flow rate in minus the flow rate out. We have a differential equation where the initial condition is that at time equals 0, the mass equals the initial mass in the tank. Of course, the flow rate in and flow rate out can each be functions of time. Now, we can also write a mass balance for a component, so we can imagine that we have a volumetric flow rate in, and the concentration coming in is C0, and we have a volumetric flow rate out, which can be different, concentration Ca, which is different, but this concentration Ca is the same as the concentration in our tank because we're assuming we're stirring this. So we can do balance on each of the components when we have a reaction. And so, for example, if we have the reaction A reacting to B, and the rate of reaction, say, is second order, so rate constant, concentration, that's the reaction rate per volume, so then we have to multiply by the volume in the reactor. The transient mass balance is total amount of that component in the reactor at any given time, so the concentration times the volume is equal to the fact we have component flowing in Ca0, and then we have volumetric flowing rate flowing out, which may be different, times the concentration leaving. The concentration leaving is the same as the concentration inside the reactor because we assume it's well mixed. And then we have A concentration times the volume, where the initial conditions, namely at T equals 0, concentration in the reactor is some initial value. This is different from the feed concentration, and it's something that changes with time. We likewise could write mass balances for component B, and if there's other reactions, those species also.